All right, hello everyone. We'll be going over this week 8 worksheet on question number 2 for dynamic programming, and we're finding the number of unique BSTs given n unique nodes, each with different values. So knowing that they're unique, we don't have to consider the cases where the values are the same. Uh, that case would make the problem a little bit complicated, but not too much. But we don't have to worry about that. What we can do is we can consider the first case, the base, like the base cases. For example, if there are no nodes, then there's only one possibility. So we can say PP0 equals 1. Um, if there's only one node, then the BST is just the node itself, which is only one possibility, which is just 1. Okay, yeah, those are the cases. Um, what about the case where there are two nodes? Let's say 1 and 2. So we can let 1 to be the root node, and then we would have something like this. Or we can let 2 to be the root node, and then we'll have something like this. Right, so what we can see is that when we're given n nodes, letting each of the n nodes to be the root node creates different BSTs, because it's impossible for the BSTs to be the same if the root node is different. So we know that if we divide it by those cases, we would create disjoint cases. So each case of having a different root node is disjoint. And we also know that every single BST has to include um, a root node, and the root node has to be one of the node from one of the cases. So it's not only disjoint, but it's also exhaustive. Okay, so knowing the two facts, if we can find the number of BSTs given a root node, then we can just do that to, we can just let every node to be the root node and count for each of them and sum it up. And that's exactly what we're gonna do. If we're given n nodes, so we have 1, 2, 3, 4, 7, all the way to n. In this case, we can let each node to be the root node. For instance, if we let 6 to be the root node, we have 1 through 5 to be on the left side of the BST of the root node, and 7 to n on the right side. So what we can do is we can find how many BSTs there are in 1 through 5 and how many BST there are in 7 through n. And the way we do that is because we would build it from smaller up. So we also always know that when there are n to be found, we would always know that when there's only n minus 1 node or less, how many possibilities of BSTs there are. And that's basically the whole idea of dynamic programming. So after we find the number of BST right here and the number of BST right here, what we can do is that we can multiply them together, because by multiplication principle, the number of total possibility would just be the number from the left times the number from the right. So we have to set 1 to be the root node, and in this n minus 1 node, we count the number of BST, and we set 2 to be the root node, and for 1, count how many BST there are in one element, and how many BST there are in n minus 2 elements. Yeah. So to ensure that we know the number of BST from 0 to n minus 1, we have to build from 0 up. So when we calculate dp2, where there Yeah, so this is a case where there are two nodes. What we can do is we look at one and we see that there's nothing on the left, and dp0 is 1, so this is the only possibility, is nothing. And dp1 is also 1, and on the right side there's only one node. So let this to be the root node gives you 1, and let this to be the root node gives you 1, so that gives 2. So dp2 would equal to 2. And we'll do one more together. Let's do dp3. We can first let 1 to be the root node. If we let 1 to be the root node, on the left side, there's nothing, so there's only one possibility. And on the right side, there are two nodes. We already know two nodes. We have two different BSTs. So for 1, it would be 1 times 2, which is 2. And for 2, if we let 2 to be the root node, we have 1 on the left and 1 on the right. And we know that with one unique node, the number of BSTs is 1. So in this case, it will be 1 to the left and 1 to the right. So it's 1 times 1 equals 1. And by symmetry, 3 will be similar to 1. It will be 2 times 1 equals 2. And the total we have is 2 plus 2 plus 1 equals 5. And we can build this all the way up for until we get dp of 1. And yeah, that's about it. So at first you should initialize an array of size. Let's walk it through. First, initialize array of size n plus 1 for the case of dp0 as well. And then fill in the base case of dp0 and dp1, which is 1. And for the rest, dpi, for any I from 2 through n, it would be sum of j going from 1 to be the pivot all the way to I. Actually, it should be 0. 0 to I of, let's think about it. So the first one's, actually let's do 1 to I inclusive. So we first let the first one to be the pivot, and that would just be dp of I minus j times dp of j minus 1. So this will be the left side, and this will be the right side. If we add it up together, we get I minus 1, which is the total of elements, I minus 1, because you're not including yourself. And yeah, you just sum up every single case up to I. You keep building the array all the way up until you reach the end, and you can just return dp of n as your answer.